So for my hot wash video for this unit, I'm going to talk about the phosphoinositide pathway. So first, here's some background on G-protein coupled receptors. So G-protein coupled receptors are intermembrane receptor proteins that are coupled to an intracellular G-protein, and they're usually made up of 7 alpha helices that are in the membrane. These G-proteins, they come in many varieties. They're not just one type. And all the different varieties, those are going to create different signals in the cell. So for this pathway, it's going to be GQ, and it's a heterotrimer. And most importantly is this alpha subunit, which is bound to GDP, but it can also bind to GTP, and when it does that, it breaks off from the other subunits and goes on to create a cellular response of its own. So specifically for this pathway, our ligands are going to be epinephrine and norepinephrine, and it's going to bind to specifically an alpha adrenergic receptor, is the most common one. This is what it looks like in the binding site of this receptor, which is extracellular. So this ligand binding is going to cause a conformation change in the GPCR, which is going to lead to the G protein on the other side dropping its GDP and binding to a GTP, and that's going to cause enough strain here because GTP is just ever so slightly bigger than GDP. It's going to break apart, and now it's active and it can go on to activate other things. So primarily what it's going to activate is this phospholipase C. And here you can see here, this is the activated GQ subunit. It's going to come and bind to the phospholipase C. And what the phospholipase C is going to do is it's going to cut up this membrane lipid known as phosphatidylinositol 4,5-bisphosphate. As you can see here, it has this lipid tail and this really polar sugar head. So the phospholipase C is going to cut it up, and it's going to leave this diacylglycerol in the membrane. And then the inositol 1,4,5-trisphosphate, or IP3, it's going to also come off, and it's polar though, so it can diffuse through the cell and do its own thing. Oh, and then I left this here to show how there's so many different receptors and so many different ligands that can do essentially the same pathway in the cell. So this is a completely different ligand, it's a completely different receptor, but it still comes and is able to activate the PLC and do the same process of cleaving this lipid in the membrane. But instead of a GPCR, it's an RTK. I just think that's a little bit interesting. So one of those secondary messengers, one of the things that was cleaved is this IP3, and it's a sugar, so it's polar, and it's able to fuse through the cytoplasm as a secondary messenger. And what it's going to do once it's cleaved, here's the G protein right here, it's going to come down to the endoplasmic reticulum, it's going to bind to a receptor, and it's going to cause calcium channels to be opened, releasing calcium into the cell. Once that calcium is released, it's going to bind to this enzyme calmodulin, and calmodulin is super important. What it's going to do is it's going to bind to the calmodulin, and it's going to change its shape, so now the calmodulin is able to bind to an inactive protein to activate it, so that now it's able to go and phosphorylate things and create this kinase cascade that's going to create a response in the cell. So for example, the calmodulin can activate calmodulin-dependent protein kinase, which can activate PKB, or otherwise known as AKT, and it creates a kinase cascade. Okay, and more on calmodulin. So I was really curious about calmodulin, so I thought that I'd research it a little bit more. So this is where the name comes from. It's from calcium modulating protein, calmodulin. And I was really surprised to learn this. It interacts with over 300 different proteins as a mediator for calcium, and is a super flexible structure. So the way that it works is it works across many concentrations of calcium, and so it can bind with different proteins based on those calcium levels and turn it into a tangible signal that directs cell activity based on calcium levels. So when different amounts of calcium bind based on calcium availability in the cell, it's going to create many different conformations of the calmodulin. So it can bind in many different places and in many different amounts. And this allows it to interact with many different proteins based on calcium level and availability. So when calcium levels are really high, it'll activate different proteins than it would if calcium levels were really low. And so that will help control the protein activation and transmit that signal from just there being calcium in the cell to a tangible effect in the cell. And some of the things that it affects is endocytosis, mitosis, cell growth, maintenance of normal cell functions, inflammation, metabolism, apoptosis, muscle contraction, intercellular movement, short and long-term memory, nerve growth, neurotransmission, and immune responses. So it's really, really important in our bodies, and it plays a role in a ton of different pathways in our bodies and responses. That's more on calmodulin. Okay, what about the other messenger, diacylglycerol? So as you can see, you can follow our pathway here. The lipid gets cleaved. You have the IP3 down here. What about the diacylglycerol? So it's hydrophobic, so it's going to stay in the membrane. It's going to come over and it's going to bind to the PKC, and it's going to activate the PKC so that now it's able to phosphorylate things and create that kinase cascade that's going to create results in the cell. And I also wanted to note that increased calcium from the IP3 down here is also going to help stimulate the PKC. So they're both working together in this pathway. They're not completely independent, and they build on each other. So what are the downstream impacts of this pathway? So this process regulates many things, and that's mainly due to the calmodulin component of it. It regulates things like cell growth via regulation of glucose uptake, cardiac contraction, your heart rate, bronchoconstriction versus dilation, your immune response and inflammation, electrolyte balances, and neurotransmitter release. And if you think about back to what our original ligand is, a lot of these make a lot of sense because with epinephrine, that's going to trigger your fight or flight response. So you're going to want to have things like increased glucose that'll give you energy. You're going to want things like an increased heart rate to get you pumped up. You're going to want things like bronchodilation so that you can breathe better. And that's how it's going to affect it. It's going to go from epinephrine just binding to this GPCR to all these effects in your cell, and that's due to this pathway right here, phosphoinositol. So here are my sources, and that was the phosphoinositide pathway. Thank you.